All right, hello, I'm Brendan Mulcahy. Welcome to my talk. I'm a research engineer, and I'm the lead of the Learning Agents team. Daniel Holden and I co-created Learning Agents over the last year and a half or so. And today we're going to learn about Learning Agents. So here's what we're going to talk about today. We're going to talk about why. Why do we make Learning Agents? Why should you use it? How? How does it work? How did we use it in our Fortnite research project? And then what? What's coming in 5.5 and beyond? So if you're all here at Unreal Fest and you're an Unreal game developer, you know that we love video games. We love playing games. We love making games. We love everything about games, right? Well, maybe not everything. There are some things you probably don't like, and one thing that I particularly don't like is games that have cheating AI. So, I play a lot of competitive games, and I like to turn up the difficulty to the max, and I'm always disappointed when the AI is playing a sort of different game from the game that I'm playing. They either get extra gold, they get extra ammo, or they get extra sensory perception. But at the same time, I get it, because making intelligent AI is hard, and making it fun is even harder. So how are we going to solve this problem? Well, I think we can, but we can't get there with just classical game AI alone. What we need to do is we need more power. We need machine learning. And in particular, we need these two types of machine learning. We need reinforcement learning, and we need imitation learning. So I'm not going to cover all the details of these two things. You can go learn about that on your own online. But just really briefly to get us on the same page, hopefully. Reinforcement learning is similar to training a pet, right? You're going to give treats when good things are happening, or you're going to withhold the treats when bad things are happening. So we're going to put an agent in our game world. We're going to wire up the observations so that it knows, what's going on around it, how fast are objects moving, where are objects, etc. And then we're going to wire it up to the actions. So, it's going to be able to do stuff in the world. It's going to take random actions, and then we're going to write a reward function that is going to reward it for doing the behavior that we want it to learn to do. And as it randomly stumbles upon those rewards, it's going to get reinforced, and it's going to want to do that action more and more until it's no longer doing random actions. It's doing what we were trying to get it to do. So that's reinforcement learning in a nutshell. Imitation learning is a different take on that. So what we're going to do is we're going to have something else that we want to imitate, whether that be a player that is playing the game, potentially from replays, or we might have another AI system that we already have, like a behavior tree or a state machine, that can produce actions for us. And we want to create a data set of observations around that player or that other AI. And then we're going to record what actions it's taking and make this paired data set that we can then train our neural network on. So that's imitation learning. So why would you want to use these? Well, there's a ton of different use cases, and I'm sure you can think of more than what I have on here. But these are some things that I care about. So when I play games, I want to play against bots that are human-like, especially in Fortnite Battle Royale. When I run into bots and I'm playing a game, I can say, you don't feel like a player. So we can use imitation learning to create a data set to train the bot and get it acting in a much more human-like way, and make the experience of playing against the bots much closer to the experience of playing against players. So when we put new players against bots, we can transition them into playing against humans much easier. If we can get a big enough data set with tons of different examples of playing across the skill brackets, we can customize bot intelligence, where we can put in some sort of skill level or MMR, however you want to think about it, as part of the parameter into our model. And that'll allow us to have a much more tunable experience where we can deploy bots for new players or for veterans alike. And then finally, instead of having to reprogram our bots whenever new content comes out, if we're doing a live service game, we can maybe retrain instead. There's a new map. We don't have to reprogram the bots to handle all that new stuff. We can just retrain them and trade off programmer time for some computational resources. And perhaps that's a good trade for you. So machine learning is an extremely hyped up technology, and I think we all value skepticism as engineers. So I don't want you to get rid of all your skepticism, but at least for this talk, let's just put that aside and try to learn what we can. And I want to encourage, that I'm not telling you that machine learning is some golden hammer that's going to solve all your problems. This is just one more tool in your toolbox. So I want to say, like, everything you already know about AI, whether that be behavior trees, state machines, whatever, all of that is still really good and valuable, and we want to use that where it's appropriate. And then maybe we want to use machine learning in other places where it does its thing best. So just going off the battle royale, if we have wolves or we have frogs or whatever other creatures, those things are simple. Like, it's way better to just go and program that using AI. But if we're trying to replace players in our lobbies, trying to program that and make it feel just like another human is extremely challenging. So that's where machine learning can come in. So let's use the right tool for the job. So we already covered sort of the first use case, which is I want to create AI opponents to play against that feel human-like, but also maybe I want to play against or have teammates that play in a human-like way who are bots. Perhaps that's something that could be valuable for you. Once we have bots that know how to play games, we can use them to automatically QA test. We can wire up our data instrumentation into our playtest server, gather a big data set, create a bot that plays like our QA testers. And now our QA testers maybe don't have to do so much golden path testing. They can go focus on the nitty-gritty bugs that are harder to find. And then finally, it enables us to do new sorts of games where we can be a teacher or a trainer, maybe like something like Nintendogs where you need to train a pet and we can teach it and it can learn tricks in real time. Or maybe you're the coach of a basketball team and you're helping out your agents learn how to play basketball well. So that enables new types of gameplay, and definitely you can see emerging gameplay as part of that. So let's start to get into the technical details. So Learning Agents is an experimental plugin, and I want to just hammer that home that things are going to be changing. We're going to be updating it. We're going to be adding a lot. It's fully usable today. We shipped it in 5.3, so definitely check it out. The thing that's great for you is if you want to help contribute, you can use it, give me feedback, and we can make changes and try to make it the greatest machine learning plugin in the universe. So Learning Agents is for doing reinforcement and imitation learning, and has APIs for doing these things. So you can collect data, you can train your agents, and then finally, when you want to ship your game, you can run them directly with Learning Agents. So when we set out to design Learning Agents, we wanted it to be flexible and powerful enough for technical users to be able to customize and build upon. Devs who know C++, know Python, they're not going to be having to come ask us to add features to Learning Agents all the time, because we designed it in a way where they can go add those customizations themselves. But we also wanted it to be accessible to the non-technical users, people who love Blueprints. We have the API fully supported in Blueprints, and you can do all of your training directly in the editor. So you don't need to set up some complicated infrastructure. And then finally, as I mentioned earlier, we wanted to integrate really easily with existing AI technology. So you have a behavior tree, you wanted to replace one node in that tree with a neural network, you can do that. You don't have to throw away everything and try to train your agents entirely from scratch. So sort of the flip side, some non-goals we had was we didn't want to make Learning Agents into a framework, because with a framework, we're sort of telling you that we know exactly how you need to solve this problem. And instead, we made it much more like a library where you use it to solve the problems that you care about, and even problems that I hadn't anticipated when we were designing Learning Agents. And then finally, since we wanted to create agents that are either going to run on a game server for a multiplayer game or run on an end user device for a single player game, we avoided including black box learning, such as using pixels as observations. We'll probably add that stuff back in later, but in order to steer people away from that and steer them towards using direct game properties so that you can actually get something that's going to run in your game. So for technical details, we use PyTorch. So when you're running your UE game process and you want to train, we'll spawn a Python sub process, and that's using PyTorch for training. You can do that directly in the editor, or you can cook your game and run a headless build if you need to get data collecting faster. And then when you go to ship, we fully support the neural network engine that comes with UE. And we implemented a custom backend for it called the Runtime Basic CPU, which can be used for fast cross-platform CPU inference. So if you want to run a neural network on a Nintendo Switch or on any of the mobile platforms or on a Linux server, whatever, learning agents should work for you there. So at a really high view, what does the code look like? So learning agents is built around this manager component, which you're going to drop in your scene, and then you need to register what are the agents. We're going to go through this car example where we're going to train cars to race around a track. So we'll be calling add agents to get agent IDs assigned to each of our cars. The manager's second responsibility is it keeps track of the actual program you're running, whether you're doing training or you're doing inference. And that's going to be supported by these manager objects. So this part is a little bit more of a framework where we try to help you design your program, but then you compose it yourself in the manager. And that gives you a lot of that flexibility I talked about. So we're not going to go into each of these components in extreme detail, but we're going to look a little bit more at the interactor in a bit. But you can see how these would fit into the different paradigms we talked about, whether it's reinforcement or imitation learning. So with reinforcement learning, you're going to use the interactor and the policy. And those are how you're going to hook it up to your game to gather those observations and actions. And then when you want to do your reward function, you're going to define that in a training environment. And then finally, you're going to add a PPO trainer, and that's going to be the actual algorithm that's going to train your agent. So if you don't know what PPO is, don't worry. It's still pretty easy to use. With imitation learning, you can reuse the interactor and the policy you defined, and then you're going to use a couple other components. So we have a recorder, which is going to grab those observations and actions and create that data you need to train. And when you want to figure out, like, are we going to be copying a player or copying some other AI, you implement that in a controller and implement the gather actions function. So that's how you can create that paired data set of states and actions. When we go to create the manager, it's just simply an actor component, and you can add it to any actor in your scene. And then we can call that add agents function that I talked about. So I'm going to show most of the demonstrations in blueprints. Everything is fully supported in C++, but I think looking at blueprints is more appealing in a presentation than looking at C++ code. So don't be alarmed that there's only blueprints, but the C++ API is great as well. When you want to go add manager objects, you're going to call these make functions. So we got make interactor, make critic, make policy, etc. You call those, you wire up the different settings, and then you can customize learning agents to your game. When you want to run training and inference, you can call this high-level function on the PPO trainer that'll run training for you. This is where a lot of the flexibility comes in, because you can wire that up wherever you want. If your game is like a real-time game and you're ticking, you can tick every frame of your game. You could also just adjust the tick rate of this actor, so it's only ticking maybe 5 hertz or something if that's appropriate for your game. And then if you have a turn-based game, and maybe you want to have an event where it's like the AI turn start, you can call run inference from that AI turn start. You don't have to call it from tick. So this gives you a lot of flexibility to run the neural network where you want to run it. When you're setting up the interactor, you're basically just going to override some functions. So you're going to specify observations and actions. That's sort of where you define a schema. And then in gather agent observation and perform agent action, that's where you're going to wire in the actual data that fits into that schema. We're going to look more at that in a second. And then you can see there's a similar thing with the training environment. You just override some functions. So now let's get into the really nitty-gritty details. How are we going to get the data out of our game, and how are we going to push the actions back into our game? So with 5.4, we wanted to make that easier, and we designed this feature we call structured observations and actions. So we were motivated by this question, which is how can we make it easy for game devs to specify what an agent observes and what its actions are? And I want to give you a kind of concrete example that hopefully you can wrap your head around. So let's say we're programming Jonesy bot here, and we need to wire up his observations. He needs to look at a lot of different objects in his scene in order to play in an intelligent way. He needs to look at trees, which are pretty boring. They just have a position and maybe a rotation. Treasure chests maybe have like an open and closed state. The guns have an ammo count, and then we have way complicated things like other players like Jonesy. So we need to gather different properties for all these different objects, and we need to somehow get that into our neural network. So that seems like an interesting challenge. With actions, we might have different paths that we need to go down. So some situations we want to move, in which case we're going to need to have our neural network output a direction and a speed. If we're trying to shoot, we might have a list of targets we can shoot at, and the neural network will output like a one-hot encoding of which target to shoot at. So what we're going to do is we're going to define a sort of schema that maps onto this data. And then at runtime, you're going to write code that's going to provide the observation. And then learning agents will validate that observation against the schema. And then under the hood, learning agents will generate a neural network for you that has the appropriate architecture based on the data that you defined in your schema. So we want to encourage you to spend a lot more time thinking about your data than worrying so much about the details of the neural network. So here's what that might look like in a blueprint. When we want to define the schema for our observation, you're going to do what we call specifying. And you kind of read these from right to left. So we're going to take in a set of observations where each observation is made up of a location, an enum value that maybe says if it's a chest or a tree or a player. And then you can have optional observations. So maybe for the gun, we need to know the ammo count, and we can specify that we're going to have this thing that we might sometimes have. And then here's the one C++ thing I put here, because look at how beautiful it is to define that schema in C++. Then when you want to go gather observations, you need to actually get the data from someplace, and you're going to be calling normal functions that you're all familiar with. So here we're going to create a set of observations where the only element of that set is made up of an object that has a relativized location. It's got the type of the object, and then it's either going to give us the ammo count if it's a gun, or it's going to provide a null observation if it's not valid because it's not a gun. And you can see that we're calling functions that you know, like get actor location, get actor velocity, whatever. So we don't have like a whole new system for talking to actors in the game. We just create these slots, and you stick the data in as you need. On the action side, it's pretty similar. Here we define that an action is made up of either that choice between what target to shoot at, or moving, in which we need to have that direction and the speed. And then when we want to perform the actions, we're going to pull them out of the result from the neural network and then distribute them along. So we can have a switch where it says, if the action is moving, then we're going to get a direction of speed and then apply it to the move function on our actor. Or if we're shooting, we can pull out which target it was and then call the shoot function on our actor. So a lot of that was probably hard to understand in the moment. And if you want to take more time, I highly encourage you to go check out the course that we put together. It's available on the developer community site. And if you just search for Unreal Learning Agents, Learn to Drive, you can find it. And we'll go into a lot more detail than what I'm able to cover right here. So here's what you'll be creating. So by the time you're done with the tutorial, you'll have trained a car to race around the vehicle template. And we didn't have to program this at all. It just learns how to drive, and it tries to drive as quickly as it can based on the reward function we defined. So we want to maximize velocity, and then we want to avoid driving off the track and crashing into walls and all that sort of stuff. So you can see that looks pretty good, and that's what you'll be doing there. And then this time, it's always good to stop and like think about performance really quickly, because you're probably wondering like, okay, is this going to be fast enough that it can actually work in my game? And the answer should be yes. If, obviously you can design some sort of really huge observations and maybe you could run into problems. But if you're being intelligent about what you're doing, you can get results like this. So with this driving example, we have the cars racing around the track. And for observations, we need to calculate the distance to the spline. And that takes 19 microseconds or whatever. But then actually running our neural network under the policy only takes 11 microseconds. So if you really think about it, it's only those 11 microseconds that are anything new. Because if you're writing your old-fashioned, classical AI system, you're probably still doing something like that spline calculation. So that's kind of like not something you have to think about. So we can get this to run really fast, and we can do this in real time, and it's not going to affect the frame rate of your game. And then, as you may know, if you've tried this before, there's a lot of debugging you need to do. You need to debug your regular code, but you also need to debug your data when you're training to make sure that your agents are actually seeing the things that you wanted them to see in the world. So in the vehicle tutorial, we have the spline, and then we have a set of points along the spline to show the shape of the track. And you can kind of see here what that would look like for the agent. And you can imagine in your head, like if I had those points and I was driving along, like I could probably learn to do that. And then you look at the bugged version of this and the points are all somewhere else, and you're like, yeah, no wonder they can't learn to drive. I made a mistake somewhere. So this is a powerful tool. Definitely check out the visual logger. Can help make debugging way easier. And that is covered in the tutorial. So then we want to look at a research project we did with learning agents in Fortnite. So this paper is human-like behavior in a third-person shooter with imitation learning. It was presented this summer at the IEEE Conference on Games by our intern, Alex Farhang. And we'll go into more details about how this works. So in Battle Royale, player bots should do these two things. One, they should prepare players to play against other players. So we want the bots to play in a human-like way so that there's not a stark transition of playing against bots and then you play your first match against humans and it's just like completely, you get destroyed because you weren't even ready to play the game really. So if we had the ability to have our bots scale in difficulty up to the point where you're ready to play against players, that could really create a great experience for players. And then sort of along that line, we want the bots to be able to adjust their skill so that if we have veteran players coming back, we can put them with bots and give them a reasonable challenge that they're going to have fun with. So we're going to try to solve both of these problems with this paper. So if we look at the existing Fortnite bot AI, it's going to look somewhat bot-like. So let's take a look at that. So you can see Jonesy was going to pick a point, sort of intentionally missing you, and then he's going to jump around. And if you've played Battle Royale and you're faced Jonesy, where you'd be Emmy in this case in the background looking at Jonesy, it's pretty easy to tell that Jonesy's not another player. So how can we solve that? So what we wanted to do is we set up our own data gym. Basically, we made a level where it's like a 1v1 fight, and you're gonna play as Emmy, and you're gonna be shooting at Jonesy, and he's gonna be fighting back against you, and you're gonna hopefully take him out. He'll respawn at some place and it'll reset, and you can play for 20 minutes and collect a bunch of data. And we could put other people on our team, play through this, collect a data set of a bunch of different people, and we're gonna log that off into files. So we're gonna collect those observations, collect the actions, and make a nice little data set there. And then we did offline training in Python. So we created a neural network, trained it up. Then we grabbed our network, brought it in to learning agents, dropped in the editor, and we're able to watch, how does that model play the game? Does it look like how a human plays it? And then furthermore, we can run the same data collection on that model in order to generate some stats so that we can, quantitatively compare how a human plays with how our model plays. So anyway, that's how the data gym works. Here's how it works with learning agents. So we're going to have Emmy add herself as an agent to the manager. And then we're going to use those components we talked about earlier. So we create an interactor where we define the observations that we need to play Fortnite. So an offset vector to the opponent, Jonesy in this case. We had some versions with trees, so we might have locations of trees nearby. And then we have the actions of controlling the pitch and yaw of the gun, controlling crouching, jumping, the fire rate, looking down the sights, and moving around. So basically everything you could do for combat. And then we're going to run the recorder, grab all those observations, all those actions, create that data set. And we can drop those offline in just some files that we can read somewhere else. So we needed to pick a model that we wanted to train. And for this paper, we didn't want to have like a super, we didn't want to go through a ton of different models. We wanted to pick something powerful and just kind of iterate with that. And you'll see why we did that in a moment. So the model we chose is this causal transformer, which if you're familiar with LLMs, it works kind of similar to that. So we take states and actions, which are represented in these arrays of floats. We basically embed them into tokens. And then we're going to feed a sequence of tokens representing different times, right? So we're going to have 60 frames of data, which is about 2 seconds of gameplay. And then we're going to feed that into the model every frame. And then the model is predicting the action for every single one of those time steps. And we can train it by comparing the action that the player took to the action the model predicted, and that's how we're going to train this. So when we're doing inference, we train this outside of the editor in Python, and we output our model into the Onyx format, which you're maybe familiar with. That is fully supported in the neural network engine. So we can just take our Onyx model, drop it on the editor, do a little bit of some programming, since Learning Agents out of the box doesn't let you run Onyx models, but it's only a few lines of C++, you can wire it up. I'll get that added in there eventually, so you won't have to do that. And then we can run our policy, and then take that existing interactor we use to gather the data, and just reuse that component when we're doing inference. So here's what our result looks like. You can see that Emmy knows how to move around, knows how to control the gun, knows how to do the triggering. And then the way it moves around in the space looks a lot more human-like. It misses very naturally, and it is able to shoot pretty well. So that was our first result. And then, like I mentioned, we can do some sort of quantitative analysis by basically running the model in the same data gym, and then we can take those results and compare them offline. So here's some stats we took. So in the orange, you could see if you had 2 of the AI bots fighting against each other, they end up with a 50% win rate, which is totally expected. Humans are quite a bit better than the bots, so you can see that they have a really high win rate. And then you can see that the neural network we trained is able to achieve a higher win rate than random. And you can see that that sort of trend continues with kills, accuracy, et cetera. But those high-level stats don't really tell a full story of, is it human-like? It just tells you, okay, it's better. So we need to look a little bit closer, and you can look here on the bottom and see that when you're acquiring a target, so that's when you're doing this big movement from, like, I'm looking over here and I'm trying to shoot somebody over here. You can do this big movement, and you can see the yaw error changes like 100 degrees there. You can see that the bot does it in such a way that it's jumping around a lot more, and the human and the neural network are varying their movement in a much smoother way. And that's what gives it that human-like appearance. When we're tracking a target, so that's when our crosshair has gotten close to the target, and we want to just keep on it while we're pulling the trigger. You can see the neural network and the bot have different behavior as well. The bot sort of jumps around and has this quick transition between things it's looking at, but the human and the neural network sort of smoothly move around the space. So we wanted to take this one step further, and we wanted to see what else could we do with this model, since it's pretty powerful. So if we split up our data into different groupings, we can train different ID tokens, and we can use those as a prompt to the model in order to allow it to have different behavior. So this sort of solves that problem of, I want to be able to have the ability to influence its skill. So what I could do here is I could group my data into a low skill group and a high skill group. And then I could also do something like this. I could split it up where every player is in their own group, and I can create an ID token that way. And then I'm going to learn this ID token to try to match the behavior of just that group. I'm going to feed that in sort of like a prompt in an LLM, and it's going to allow the transformer to know like which group it's trying to imitate. So you can see the top-bottom comparison here of the high skill versus the low skill model, and take a close look at this. So you can see the high skill model tends to not miss as much. It's going to get kills a lot faster. The low skill model is going to drift around the space more, and it's going to do that in a believable way. And it's going to take longer to get kills, which passes the sanity check of what we were trying to do. And then we wanted to look at our individual skill IDs and say, are we able to replicate individuals in our database? And it's a little bit hard to tell, like if you had data of me playing and someone with a similar skill level to me, what makes it play like Brendan or what makes it play like them? It's hard to do that. It's hard to tell what's different. So we looked at some high level things like how much is one player crouching versus another, and does the neural network reproduce that? So you can see on the left here that if we grab those high skill human data and then train a high skill neural network, they somewhat closely match each other. And then if we do the same with the low skill data, you see the neural network also decreases its skill. And then, like I was saying, with the crouching and jumping, we can look at individual humans in this set and see if the network reproduces that. So you can see that for the human 1, they don't crouch very much. Their neural network doesn't crouch that much. With human 2, they crouch quite a bit more, and their neural network crouches a bit more. You can see it doesn't work 100% of the time. For some reason, this third individual, they crouch a medium amount, and their network didn't crouch at all. So it's not perfect, but this is interesting because it shows how we can create bots that have different personalities, and then every single bot that the players run into don't have to behave exactly the same. And I want to remind you that this is running entirely in the editor using the neural network inference engine and using Onyx. So there's no Python at this point in time. It's just basically pure C++, and you could ship that in your game. So here's some takeaways. Imitation learning works. You can create a real-time model. And one of the best things is you can do it with a really small data set. So we collected only 8 hours of data in order to train that model. So it's something that pretty much anyone could do. You could be an indie game dev studio. You don't have to have a Fortnite battle royale amount of data to do this. It's not some sort of like science fiction to you. It's something real. You could do this right now. And then we wanted to show with the ID prompting that you could get the neural network to do anything you want it to do, really, as long as you can group your data up. So if you can get a bunch of skill buckets, you can train a bunch of ID tokens and have that tunable model. Or if you want to have that personality, you could group your data up that way and be able to prompt your model like that. And you could do whatever you can think of. So I put those question marks there. It's like whatever you could think of, and you can group your data. You can probably get the model to reproduce that. So finally, what's going to be coming in 5.5 and beyond? So a big feature we've been working on is re-architecting the training code. Going to look at that more in a moment. We've added more network protocols. I've added this thing I'm calling bring your own algorithm. For those who are more ML researcher inclined, you can add in things beyond PPO. And then finally, we got Mac and Linux training working. So for the training re-architected, it's a little bit small, but basically we used to have this huge make trainer block, and it didn't really have a lot of customizability to it. We broke that up. So now you got your training environment where you define your rewards and your completions. And then we have these functions like spawn the socket training process, make a socket communicator. Those allow you to control when that Python process is going to spawn under the hood. And then you call make PPO trainer. And you can see that that leads into the bring your own algorithm, because now you can call like make whatever your algorithm is trainer instead. For the networking protocols, previously we only supported shared memory, meaning you had to be training basically a Python process on the same machine as where the UE process was running. But we added the socket communicator so that you can have your UE process talking to a trainer that's running on a local area network. And then with bring your own algorithm, we added the ability in the settings where you can pass in the name of a file. So by default, you got your train PPO, which is going to run your PPO algorithm. But if you want to implement any of the other popular ML algorithms, you can do that in your project's content Python directory. You don't have to go modify the plugin anymore. And then finally, we got Mac and Linux training working. There's a bug on Mac with the shared memory. Turns out the engine doesn't actually have an implementation of shared memory. So we got a ticket filed for that. Hopefully we can get it done in the future. But you can at least train something using the sockets. And then finally, we got both of those things supported on Linux.
And it does work.
Oh, it works. So here's what's going to be coming in the future. We want to get training scale out. So currently, if you want to scale out your data collection for reinforcement learning, you have to have several gyms all existing in a single UE process. We're going to make it a lot easier for you to spawn a bunch of UE processes and be able to run those on virtual machines or containers. Or if you have a beefy workstation, you can spawn a bunch of UE headless processes and have them talking to a single Python trainer. So that's going to get your training results much faster. We've got a nice prototype of that worked out already. So instead of taking 2 hours to train the race car gym, you can get that down to 5 minutes. So that'll save you a lot of your real life wall time. We're going to work better on doing an editor integration. So having a custom toolbar where you can click and spawn these different scenarios of like how many training processes I want to have, how many data collection processes, et cetera. And then try to reduce our need to have TensorBoard. So maybe we'll have a nice GUI for you to look at there. And I want to remind you that these are things that we're currently thinking about, and there's no guarantee that these things are going to come. But I really want them for myself, so we'll probably get them added in there. I want to take a look at imitation learning and get that all fixed up. Currently, when you're creating these data files, they're in a binary format. If you want to go read those in Python or some other language, you have to know the structure of that data. It's kind of annoying. So we're looking at maybe doing flat buffers. So you have the ability to generate your Python code for reading that data out. So that should be a huge usability improvement. And then we want to integrate that with the editor so it's easier for you to do your imitation training directly from the editor and not having to always click like run game and have that. So that experience should be a lot better. And then we've got various other features that we're constantly adding. So one I wanted to highlight is action masks. A lot of times in games, maybe you have a character that's able to shoot and then they can get in a car and they're going to drive it. And they have actions like steering and pushing on the throttle and the brakes that aren't always valid, like when they're walking around in the world. So action masks are going to give you an easy way to tell that to your neural network. So it's only going to output actions that are valid for the current situation the agent's in. And then we're going to be doing a lot more stuff. So offline reinforcement learning I think is really cool. There's been some awesome papers on that. That's something I think we can get supported in the near future. And then just a quick call to action. If you thought any of this is really interesting, I highly recommend going to the course, going through it. It probably takes only about 2 hours of time to go through all of that. So that'll get you up to speed really quickly. And then if you have any questions beyond that, I'm happy to answer them at this point in time. Or you can catch me in the hallway or shoot me an email, whatever you want to do. So thanks for your time and attention, and I'll take questions.